Hello, fellow ham radio operators around the world. Here is something to get excited about. It's called the Fast 40 60 80 antenna by COMPACTenna. I'm Dr. Jack Nilsson, Dr. Jack, and this is a small, high-performance HF ham radio antenna. Now, before we get into it, a lot of you are already thinking, wait a minute, I have questions. So let me pose some of those questions that I'm quite certain many of you are already thinking about. One of the questions is about other antennas. Other antennas that I have designed and produced. Certainly there's the VHF, UHF antennas, 2 meter, 440, 220, etc. And they're very well received and very high performance for compact size, COMPACTenna. All right, both mobile and base operation. I've also created and produced some novel HF antennas in the past. Yes, even, certainly 10 meters, 20 meters, even 40 meters. They were very, very small. The one was called the 2040 Micro. It was in a 2-gallon paint plastic can, polymer plastic can, and it was very good performance for its tiny size. But what I wanted to do here was something very novel. I had some visionary thinking on producing an antenna for HF that was a little bit bigger than micro, but still very stealth. Okay, we're only talking about 5 feet tall, taking up a couple of feet wide, a couple of feet long. That's it. Very stealth, but certainly high performance, substantial performance, regardless of size. That's important. All right, so we go back to the questions. Why those bands? Yeah, why those bands? Why 40, 60, 80? Well, 60, of course, emergency communications. It's a big part of ham radio operators, but 40 and 60 or 40 and 80 meters. Well, because I wanted to create something that had activity, it's a good word, throughout the approximate 11-year sunspot cycles, including at the nulls, right? So certainly we see typically, and of course things change, but the ionosphere refraction, propagation characteristics change and are overall substantially down at the nulls and the cycles. And of course there's the atmospheric conditions, right? So noise and whatnot. So when we look at the 10 and 20 and even other bands at the null of the cycle, certainly much less activity. But if we look at the 40 meter and the 80 meter and the 60 meter bands, we see we can use the definition still active at the nulls. So throughout the sunspot cycles, so you don't lose a few years in there where things are more intermittent. That's why. All right, well that's good, but then the obvious question, isn't it extremely difficult to create small and convenient antenna for 80 meters? Yes, it is. Yes, it is. I mean, there are 80 meter magnetic loop antennas, but very low efficiency. I'll talk a little bit more about that later. You have to constantly retune, and typically they don't handle much power, plus they're substantially expensive. So yeah, there's some drawbacks. Isn't this my idea always of having an antenna that you don't have to do a lot of tuning? Be broadband and 80 meters. Isn't that and small? Isn't that extremely? Yes, it is. But with visionary thinking and very diligent engineering, I was able to do it. That's why I said this is something to be quite excited about. All right. Another question, high performance in a stealth antenna. Yes, absolutely. Not just great for tiny size. Good performance in a very small size. Broadband. Yes. How do you do that? 40 meter, 80 meters, much less 40 meters. How do you do that? Yeah, that's you have to be innovative. You have to do something entirely different. Yeah. All right. No tuning of the antenna structure. Yeah, that's what I'm all about. There's no tuning of the antenna structure itself here, and I'll get into that in a little bit later. Easy to deploy? Absolutely. In fact, on the specification sheet, 5 pages, they come in a very nice folder. I use the word immediate. Installation, assembly is immediate. There's really only 3 basic pieces, and they're stainless steel wing nuts and brass thumb screws. So no tools necessary. All right? And you know, it's not just for temporary installation like POTA, it's also for permanent installation. Everything is UV stable. Even the yellow UV stable high visibility wire we'll talk about, and the white, the high grade white coaxial cable included, extension cable included with this antenna, UV stable, high visibility. But high power watts, really? Really, Dr. Jack? High power watts as well? I mean, look at what's out there in small sizes. No, whether it's loaded antennas or magnetic loop antennas, no, they don't have high power except for very few, and quite pricey, understandably, but they are. All right. Well, before I get into some explanation of this, and I'm just going to go on the surface level in terms of physics, in terms of circuit equivalence and these kind of things. Let me just show you what it looks like. What does it look like? What does it look like? I gave the size, but what is it? It's less than 5 pounds total. What does it look like? Well, this is what it looks like in my backyard on the mulch. You can see it's even shorter than the decorative fence. There's a lot to it in terms of science, but that's basically it. It's easy. It's great. All right. Let's get into it a little bit. A little bit of the explanation, and then I'll review the specification sheet at the end, basically. All right. So, yes, we have to be innovative. We have to be visionary, but we also will use the qualities of various existing antenna designs. There's a lot of different antenna designs, and there's various qualities of each of these that we can pull from. Right? There's the quarter wave. Overall, very efficient. We have the short-loaded monopole. Yes, less efficiency. It's a nice little design. Bandwidth starts narrowing. Yeah, okay. Half-wave dipole, very basic. It works. Height above ground and the horizontal, well, regardless, makes a big difference in the elevation coordinate pattern, right? And then we have the off-center fed, very nice and increasing wideband characteristics within the band that you're talking about. Some of them are multi-banded. All right, so that's nice. We have the sloper. You can see you have the dipole there at a certain angle from the ground. That helps in terms of taking something that's bidirectional and turning it into more omnidirectional, as well as other things. Again, I'm just going to skim things here. I want this video not to be too long. I'd like you to see the whole thing, if you have a few minutes. Then we have the end-fed half-wave, very interesting. That's the transformer, various configurations of that transformer. That's an interesting design. We have the small magnetic loop. We can see how small it is there. Yeah, and yeah, that's nice for a very small antenna. But again, low efficiency. Now, earth coupling. That's a very interesting subject. Earth coupling. All right, and a little bit of novelty here. All right. Okay. All right. I mean, I just say briefly, we've always seen antennas with really long radials, and a lot of them, right? And then more recently, some people try to use the mesh type of a thing with various levels of success on that. This is different. All right. And then also prior HF designs, like I talked about already. I'm going to pull from qualities of those as well in this overall design. I do want to then finish looking at various small antennas that are well known. All right, I'm not talking about my other designs at this time. We have loaded monopoles, okay, and we have magnetic loops. Narrow bandwidth. Yeah, all right, I addressed that a little bit. Again, we want something easy to deploy and easy to use. It needs to be broadband. I mean, that's almost like an impossible thing, right? How do you do that? Yeah, how do you do that? All right, we're going to get to it. So the small magnetic loop, you've seen this before in one of my other video presentations, the various feeds, with a very low impedance, it needs to be matched. These are lump parameters of doing it in different ways. The reason I'm showing this again is because we see some circuit equivalence here, and I'm going to lead up to the circuit equivalence, the approximate circuit equivalence of this antenna, to give a basic explanation on how you make this very broadband. And it's not just that, but that's a big part of it. All right. So, all right then, how do you make a small antenna broadband? Well, certainly you have experienced and is well received, and thank you so much, the VHF, UHF antennas from COMPACtenna, the 2 meter, 440, 220, etc. Yes, but we're talking HF now, okay? So, all right. Well, let's look at some broadband things that are out there, some of which you already know, and may or may not know the circuit equivalent, all right? One of them is your coaxial cable, or your ladder line, or your twin lead. Or there are transmission lines. This is also very important on circuit boards, transmission lines. There's various types. It's a very important science and technology. All right, so here's your basic transmission line LC circuit. Inductance, capacitance, inductance, capacitance, inductance, capacitance. Let's go another step. We talked about broadband. Let's look at a broadband matching network with staged LC sections. What does that mean? Well, that means, as you can see here, we have a lower inductance, higher inductance, lower capacitance, higher in capacitance. All right, so we're moving in the direction. All right, all right. What about bandpass filters, bandpass cavities? Yes, there are various of those designs. Yes, that's good. What about the lump parameter type? All right. Well, certainly there's the elliptic, and there's the Butterworth. This is a Chebyshev. This particular Chebyshev bandpass is a pi filter. N equals 5. That means fifth order. 1, 2, 3, 4, 5. Okay. And this is an example of the S11 and S21 you would see on your 2-port vector network analyzer. What we see here is that we have the broad bandpass at various frequencies, all right, and the skirts here. These are filtered, right? And there's insertion loss. And this is the S21. So this allows those frequencies to come through. Very basically, I thought I would address this for some of you. When you have an inductor, when you have an inductor and a capacitor in series, you're tuning, you're allowing for a particular frequency. All right, so that makes some sense. And then when you have them in parallel, well, then you're creating a high resistance. So you're creating pass-through, but then resistance to here, but then you're allowing pass-through of frequencies outside of that band. It's a very simple explanation, and there are various inductor and capacitor values here in order to create this characteristic. But I thought I would address that briefly for a few of you. All right. How do we go from that over to the fast 40, 60, 80? This is how. This is the approximate complex circuit equivalent. This is the basic drawing of the antenna itself. Remember, this is what it looked like. Okay, let's go from there over to here. What have we here? Well, we have the coaxial feed. All right. Here we have a capacitance plate. Here we have the larger plate below it, which is USA. There's capacitance here. And then we have earth ground, and we have a capacitance there. We have overall interaction, in fact, RF interaction. So that's that side. Let's look at the other side. Well, essentially, we have a loop here. It's a squeezed loop. It's a compressed loop. That's important. But also important is we have a coil in that loop. We have a loop with a coil. Yeah. So what are we doing here? Well, we have that portion of the antenna, and then separately we have an L-shaped, keeping the height reasonable, plus other capacitance characteristics. We have an antenna that's essentially two parts, and the one part of it focused on the magnetic field in the near field, and the other the electric field in the near field. Now, you may have seen, it's linked on my website a little bit from the top on the home page presentation, and I talk about the Niels Bohr and the Einstein of things with antennas, and I talk about the quantum physics of Niels Bohr in the magnetic near field, and the Einstein portion in the far field, the electromagnetic field, because in the quantum side of the near field we have the magnetic and we have the electric field components, and then those essentially generate in the far field the electromagnetic RF propagating antenna at the speed of light, and that's more the Einstein side of things. I have a presentation that talks a little bit more about that. All right, let's get back to this. So we have, two significant portions of the antenna. This is all important in creating this broadband, high performance, stealth, easy to deploy antenna. All right. So let's look at the circuit. Well, look. It looks a little familiar, doesn't it, from the prior pages? Broadband filter, yeah? All right, this is the other name I used, the juxtaposed loop. So this is the interaction between the loop coil and the other side of the loop. Now note that the loop coil has both inductance as well as interline capacitance. So that's in there. It then has inductance and capacitance along it with the other side of the loop, which is connected to ground. That's where the stainless steel thumb screw comes in. Easy. Also, with that loop though, the rest of the loop, we have the inductance of the non-coil part of the loop, and of course the resistance, radiating resistance of this magnetic field portion of the antenna, which is of course very low, just like with magnetic loop antennas. Right? Then secondarily, again, magnetic field, electric field, we have the capacitance that you see in a shortened electric field whip style antenna. That's inherent in that. And you have, so that's C, radiator, electric field. And then we have the resistance of the radiator, the electric field, the radiator, the whip, which is small. Not as low as the magnetic field, but small. Right? We talked about that earlier on standard designs. Well, when we incorporate this circuit, we wind up with broadband characteristics. It's a beautiful thing. Yes, we do have a capacitance here, and we have the capacitance to ground there. Yes, that does play a role in getting this tuned properly. A substantial role, actually. But yes, and what are the dotted lines? Well, those are the yellow wires. Yeah, those yellow wires, I'll explain in a moment, are typically not used in outdoor installations unless, no, typically not used. They're used typically when the earth RF interaction and conductivity is very low, but more importantly, or more commonly, when the antenna is placed in an attic, for example, and you need increased RF interaction to ground of the earth, increased capacitance, increased RF interaction overall. All right, so that's pretty simple. Either you don't use them most of the time, or you use them. It's kind of easy. All right. This is the specification sheet. It's 5 pages long. It comes in a nice project folder with each antenna. And I've explained a lot of this already. The cycle, the use, HOAs, home, discrete, small, high-performance antennas, such as in the backyard or in an attic. POTA, Park on the Air, 60-meter emergency communications. Very good. This just shows the various components here. All very high quality, and that's RG8X, high quality, very visible white, UV stable. There's the yellow wire, the thumb screws, the wing nut here. Here we have it out in the grass as opposed to the mulch. And here we have it in the attic, and you can see the 5 foot and 10 foot high visibility yellow UV stable wires are extended. All right, and so what kind of SWR? Let's finish with this. What kind of SWRs do we see? What do we see in practice? Well, performance is really good. Let me tell you that first. You hook it up, and as long as conditions are semi-reasonable, you're going to see a lot of activity. And I need to make a quick comment about watts. Again, a lot of your small magnetic loops, especially at the lower frequencies, 40 meter, 80 meter especially, very low power, all right, typically. This is 500 watts. It will handle the watts, 500 watts PB, single sideband voice, and a little bit less, and it describes that as you go towards the digital communications, all right? So what actual SWR in closing do we see? Well, here we see on it's a Rig Expert, you can see that. A nice unit. This is an expensive VNA over here, 2-port. Here we have 2-to-1 and just a little bit below. There's your 80 meter band, your 60 meter band, your 40 meter band. Yeah, nothing's been done. It's just been hooked up, and that's what you see. Okay. I do want to make a comment. You might be wondering what this is. This antenna also, every component, very high quality. It comes with very select, high quality snap-on RF beads. Very select, okay? 20 of them already installed on the coax, and then 10 additional for you to put at your transmitter, your radio, your amplifier. Why? Because with every antenna, with RF, it comes and it comes down to the shield of the coax and makes its way back to the radio, and that can cause certain non-favorable things. So you need those RF beads, and they're expensive, but there's 10 quality ones provided for you to put at that end. All right. All right, I needed to get that out of the way. So here we see a little bit below 2 to 1. We see it climbing up to just under 3 to 1 here. That's in the 80 meter band, up around 3.9 megahertz. Here it's even a little bit better on that high profile 2-port VNA. Then when we hook this up to, for example, in this case, an ICOM 7300 with internal tuner, very nice. Look at this, 40 meters. I mean, almost flat throughout, and still below 1.5 to 1 in the 80 meter band. Of course, you always start at a frequency. You pick a frequency where the SWR is less than 3 to 1 for the internal tuners, because typically that's what they're able to do. So should you use your internal tuner? Yeah, if you have an internal tuner, use it, sure. I mean, even if it wouldn't be particularly necessary at any particular frequency, yes, use it anyway. Less RF coming back to the transmitter, to the finals. Okay. Do you ever need an external tuner? Yes, I even talk about that, like LDG auto tuners, an example. Yes, sometimes you do, because listen. Again, I talked about the earth characteristics in your area, but there's also the surrounding structures. Yeah, and let's just look at the near field, for example. And what do we mean by surrounding structures? Even trees, yes, with the water and the phloem and the xylem. Yeah, it's going to have an effect, a parasitic effect in the near field. Much less the buildings, the wires in the buildings, and these kind of things. And what is the near field? Well, it's 2D squared over the wavelength. And what does that mean? Well, depending on certain size parameters, what we're talking about is you certainly have a prominent near field, typically at the half wavelength. And how much is that? Well, at 40 meter, it's about 60 feet, and my gosh, at 80 meter, about 200 or 120 feet. Wow, yeah, that's pretty far away to have interaction. Substantial, yes, it is. By the way, a little bit less on shorter antennas. Okay, but it's there, and when you look at the near field. Potentially extending to 2 wavelengths, well, now you have structures very far away that can affect it, but it is less so at 2 wavelengths. All right, so that's a factor. Sometimes just moving the antenna a little bit can have an effect, depending on those surrounding structures. And of course, if it's in the attic, well, what can I say? All right, but yeah, I, as well as others, have had great success in a variety of installations, both temporary and permanent. So those trials have been done. So sometimes, yes, 80 meter, it's not uncommon to see, particularly at 80 meter, that you will see SWR hovering in the 4 to 4.5 area, and then an external tuner is needed. External tuners will frequently match up to 10 to 1 even. Yeah, so no problem. I got a little bit more detail because I wanted to explain a few things to some of you in the audience so that you understood it better. I think that summarizes why this is truly something to be excited about. Fast 40, 60, 80, fast to deploy. And very important in POTA, emergency communications, but also for permanent installations. So stealth. I mean, so stealth. And so small. Not micro, but small. And very high performing and broadband and easy to use. And it handles the lots. I mean, what more could you ask? And have HF operations throughout, the cycles of the sunspots. I mean, it's kind of a dream come true. And even 80 meters. Wow. All right. Thank you so much.